specialty and fear and obsession is with small probabilities. We don't quite understand small probabilities. Let's discuss a point. You ought events we just saw should happen every 10,000 years, 100,000 years, 10 billion years. Some faculty here in this university had an event and they said, oh, this 10 sigma event should happen every, I don't know how many trillion years. So do you realize how worrisome it is when someone makes a statement like that? It should have happened every 10,000 years, particularly when the person isn't even 2,000 years old, you see. So the fundamental problem of small probabilities is that rare events, they're rare. Okay, so when someone makes a statement, this in financial markets should have happened every 10,000 years, visibly, they are not making a statement based on empirical evidence, okay, or computation of the odds, but based on what? Some model, some theory. So the lower the probability, the more theory you need to be able, to compute it. Okay, typically it's something, mechanism called extrapolation based on regular event, and you extend something to what we call the tails. So my telescope problem is as follows. Consider the following. The smaller, the less you observe it in a sample. Therefore, your error rate in computing it is going to be very high. Actually, the error rate, you're computing a very, very small probability, your error rate is monstrous and probability, is very, very small. So, but the problem we have now is that we don't care about probabilities. Probabilities are something you do in classroom. What you care about is what you're going to use the probability for, which is what I have here called the lambda, the impact of the event, the effect of the event, the consequence of the event. So you're interested in a pair probability times impact, okay? So notice something is that the vicious aspect is that pair probability times effect pi lambda, as probability becomes smaller, the impact is bigger. A 1,000-year flood is going to be definitely vastly more consequential than a 5-year flood or a 100-year flood. So you care about that, and that pi times lambda becomes a lot more stochastic when pi becomes small. In other words, very, very consequential events we know absolutely nothing about, and they matter a lot, particularly in some domains in which the probabilities don't fall very quickly. So, illustration, and this is what got me into this obsessive disorder, is when I was a trader during the stock market crash of 1987, and I was a derivatives trader, okay? And the beauty of derivatives, the beauty or the ugliness of derivatives is that they compound every single error you can have because it's a square. It pays you a higher order function of the random variables. And you see here, these are the variations of a derivatives portfolio over 20 years. One day represents 97% of the variations. And that day is not forecastable, okay? So that's the problem with small probabilities. They are domains in which small probabilities are everything. Very, very small probabilities. And we know very little about them. What are these domains? There's a regular classification. I won't get into the details of how these things are made, but there's type 1 I call something that reaches central limit in real time. And type 2, it doesn't reach it in real time. The classical distinction is between things they call Gaussian or Gaussian family and things they call power law families. It doesn't work very well. It's much more effective to have what we call in real-time central limit. In other words, the rare event in type 2 will dominate the properties, regardless of... Now what worries me, I'm here, at the epicenter of education, economics, okay, Harvard. And there's something in the foundations of economics that's completely bogus, completely. And let me tell you what it is. It's not that people are rational, not rational, people keep bickering about the wrong problem. It's the fact that at the center of the techniques used in econometrics and statistics used in the center, there is this assumption that doesn't seem to hold theoretically, philosophically, this a priori defaulting to a type 1 is completely arbitrary, is unjustified, and the second one empirically. And people tell me, well, we have techniques to adjust for fat tails. Fat tails mean the contribution of the rare events. So I did the following, is not only we cannot predict rare events, we cannot even figure out what role they play in the data. And this graph shows you the following. I took every major economic variables I could find data for that covered 40 plus years, okay? From stock exchange rates, stock markets, everything that had a lot of data. Everything I could find, 20 million some pieces of data. And for most of these variables, one day in 40 years can represent 90% of a measure called kurtosis. Kurtosis tells you how much something is not Gaussian. Okay? In other words, you don't even know how non-Gaussian we are. That is a severe problem. The implication is that, well, for example, take the stock market. The stock market crash of 1987, okay, one day in 40 years represent 80-some% of the kurtosis, of that measure. That kurtosis tells you how much something is not Gaussian. So, we are in trouble, very severe trouble, okay? Even if you used another method called power law, which is beautiful on paper, much more rigorous scientifically, much more adapted to our world, we still have another problem, is that it's beautiful on paper, but when you come to calibrate, small differences in calibration lead to massively different probabilities for rare events. Very, very small, minute differences in calibration. And the errors we have in measuring what these tails are monstrous. So, measurability. Number one, that what we call norm L2, nobody should use, when you have open-ended payoff in economics, nobody should use at all something called variance, least square methods, standard deviations, Sharpe ratio, portfolio theory, even the word correlation. These don't work in domains of type 2, okay? They don't work, okay? We don't know how to measure, particularly when you're prone to, that explains why the system collapsed, because banks were using, I spent 15 years fighting risk management methods in banks. They're all based on standard deviation, portfolio theory, because they said there's some Nobels given to these names. Okay. Second point, in social science has made a distinction that I don't think very rigorous between what they call Knightian measurable risk versus non-measurable uncertainty. Several problems. Number one, when you talk about uncertainty, you don't say measuring risk. You don't measure risk like I'm measuring the stable. Okay? I'm estimating something that will happen in the future on one hand, and in the other one, I am measuring a certain, entity, physical entity, and actually the error of type 1 and type 2. The other problem is that all risks in the tails, all small probabilities are not measurable, regardless of whether you know or you know what's going on or what's not going on. So, this brings me to the consequences. Visibly forecasting, I don't know if you guys are aware, but you can check all forecasts in economics, and they don't work. Why don't they work? Because of these rare events. Because unless you, of course, don't have exposure to rare events, which for these random variables is not the case.